let me expand this along the x-axis as well. I hope it is clear to you that the high frequency component's amplitude has been brought down. But now it's kind of okay, great. That's not what I wanted to do. Maybe bring it back. Right. Now you will see that the high frequency components, which has you will be able to notice the high frequency component signal by seeing that it has a low wavelength. The high frequency constituent signal has a low wavelength, and that's the amplitude of that high frequency signal has been brought down, has been reduced by an extremely large amount, and now it's extremely small. I hope that's visible to you, and that's the operation and the behavior you can expect from a low pass filter. So let's move back to our slides. Right now, there's another circuit that we'll build. For that, we'll be using an op amp, and if you take a look at how the op amp is connected to the filter, you'll see that the op amp is connected in a voltage buffer configuration. And I asked this question from those who are present in the class, and they quite converged on the answer, and that is we use a voltage buffer of that we use a voltage buffer after the tap in point of the filter circuit, so that whatever subsequent circuit won't affect the characteristics of the filter circuit. If you don't have a voltage buffer like this and we connect some subsequent circuit beyond these two terminals, the passive circuit elements would change the impedance connected across these two terminals and affect the whole characteristic of this filter, and the cutoff frequency perhaps would move around and would not be at the actual value that we want it to be. So that's why we use a voltage buffer, and that buffer is obtained through connecting an op amp. The op amp block is available in Simscape Electrical, and just like with motors and motor drivers, we can bring in the block. Mathworks will know that it's an op amp, but it won't know what exact op amp it needs to model. And to give it that information, we need to look up the datasheet for the op amp that we'll be using and input those parameters into our block. So the op amp I'm using is a 741, and the parameters input resistance, output resistance are quite straightforward. You can find them on the datasheet within first glance. The minimum output and the maximum output voltage is quite equal to the minimum values and the maximum values of the supply voltage to this op amp. So you won't see the terms minimum output and maximum output in the datasheet, but you will be saying something like maximum rated supply voltage and its negative value. Well, the gain is quite hidden in the datasheet, and let me go back to show it to you. Just link to a doc damage page. That's what the reason was. Okay. Scrolling through our datasheet, I'm looking for an open voltage gain. I don't see those exact terms, but I see something called large signal different voltage amplification with the value 200 and the units voltage per millivolt. So I kind of think that this might be the open loop gain, even though it doesn't have that exact name. And if such were the case, then this would be 200,000. The value would be 200,000 that I'm going to put into the dialog box. Now let me scroll through to see whether I can affirm that what's given in that row is actually the open loop gain. Scrolling down until I saw a certain phrase which had the words open loop gain in it. They say that my 741 op amp has a typical open loop gain of 106 decibels. And since I have given you the expression on how to convert something to decibels, it is to take the natural log of some value and multiply it by 20, then you will have it in decibel units. So if I take the natural log of 200,000 and multiply by 20, I'll get 106. So that confirms that what they have given by large signal different voltage amplification is essentially the open loop gain. And upon that confirmation process, then I'll have to open up the other. uh, so that you had to put a 200,000 value for open loop gain. And there's one thing I forgot to mention. We have multiple options available to model the op-amp block. We have the ideal op-amp block, the finite gain one, and a full differential op-amp. In an ideal op-amp, the open loop gain would be infinite, and in a finite gain one is the block you should be using to model an actual op-amp, actual practical op-amp. Well, based on the description I gave for the reason behind using a voltage buffer, you and the circuit that I have implemented over here, you won't be able to see any difference between the results of the model given in slide 7 and the model given in slide 8. But the reason would be apparent if I were to connect any loads to the downstream circuit from the tap-in point for V out. Due to the presence of a voltage buffer, whatever I build over here won't affect the characteristics of the low pass filter, and by characteristics I will remain the cutoff frequency. So I'll leave that as a task for you, which you can do at home and figure it out by yourself. I'll be giving the model files for the models described in slide 7 and 8 as well. You can connect subsequent circuits with multiple passive and yeah, multiple circuit elements in it. Essentially, build a complex load after the tapping point for V in, which are V out, and see what happens with regards to the filtration. That's an activity that you can do at home. And apart from that, we don't have any other